Hi, everyone. My name is Avik Day. I'm the co-founder and CTO of Ghost Robotics. And I was previously a postdoc at Harvard and got my PhD at UPenn. Thank you very much for inviting me to this workshop. Through my continued work in robotics, I often come into work with actuators, whether at a robot design level, where we're trying to optimize the robot performance with respect to the constraints that the actuators present, or whether it is just improving actuators themselves. So I'm going to talk to you a little bit about the latter today. So just to give you a bit of a background on myself, I've worked on robots at many different size scales. The earliest robots I worked on were little direct drive robots at Penn in the kind of the 1 to 6 kilogram range, including this tail and leg actuated hopping robot, bipedal hopping robot called Jerboa, and a 6 kilogram direct drive quadruped robot called Minotaur. I then went during my postdoc to work on very, very small 100 milligram flapping robots at Rob Wood's lab at Harvard, actuated by piezoelectric actuators. And at Ghost Robotics, since 2017, been working on kind of larger quadrupedal robots for kind of industrial applications. Right now we have 2 products, a 12 kilogram quadruped for research type applications and a larger quadruped, about 43 kilograms, meant for industrial applications. That is the company's main focus at the moment. So a little bit about what I do currently in the company. So I started the company with my co-founder Gavin in graduate school, and right now it has about 25 people. This is the larger vision robot, which is sized about in a way that makes it kind of easier to climb and descend stairs. And one of the kind of the aspects that we really try to push on is to use kind of simple drivetrain components and try to optimize the design as much as possible. So right now what you're seeing is the kind of the smaller Spirit quadruped, and that's also uses much of the same software, but obviously is much smaller and uses different kinds of drivetrain. So we try to, as much as possible, put the complexity of the robots in software, not in hardware. It doesn't have any force torque sensors or anything, and the design is optimized for mechanical kind of efficiency, as well as computational efficiency. The limitations of our designs are, we don't usually build them to carry a lot of payload, mostly to carry sensors around and just be a mobile platform. So in terms of the types of applications we're looking at, a lot of them involve actually kind of security applications where the robot's trying to just carry some sensors around to do boring security patrols and things like that. Here it is doing such a task and coming in to autonomously charge itself. And you can see based on the amount of standing water and other kinds of just weather that the robots see in their usage. It's very important to have the robot be weatherproof, which is something we spent a lot of effort on. Yeah, so we see that this kind of application where the robot just needs to kind of mostly carry sensors around as being a large part of the initial set of applications. And we're also looking at a few applications with some amount of mobile manipulation, as you can sort of see on the right, whether it be for detecting usage in hazardous scenarios, or for bomb disposal or those kinds of applications. We usually try to optimize our designs for the fundamental constraints of specific force and power that we run into. So in particular, autonomous applications like the kind that we looked at in the previous slide, really autonomy requires power autonomy as well. So obviously that means since the robot has to carry its own battery around, its performance is really dependent on being very efficient. So the total cost of transport of the Vision 60 robot is somewhere between 0.46 to 0.8, depending on the terrain, which we think is pretty good. So among this, the majority of the power is consumed by the motors, obviously, and we try very hard to optimize our designs to minimize the power consumption of the motors while the robot is moving at different speeds. And we also actually try to lower the power consumption of the software, whether it be the software that's controlling the robot, controlling the robot's motion, or autonomy. Other than the efficiency requirements, we also tried to design our robots to not need as many external sensors, so as well as be able to be flexible enough to perform lots of different behaviors. For these requirements, we also like to have high control bandwidth and transparency of the actuators. So to just give an idea of what these are both videos from back in our graduate school days with the Minotaur robot that we built. So this robot was direct drive, so obviously the efficiency was not very good, but it was certainly a very flexible platform, whether you can see an 8-degree of freedom robot jumping up and opening a door. It had very high control bandwidth, so it can perceive that it hit the door handle and manipulate it all within a 50 millisecond time span, which is very fast. And also it has very high sensitivity. So this is without any external sensors. You can see that the motor can detect a person blowing on it and change direction. So for all these requirements that we have, usually we have to think about how to optimize the system. And kind of the way I think about the stack of components that's in play for kind of a legged robot system. There are a lot of components, as you can see here. So in terms of all of these different components, there's been a lot of work done on motor design and the fundamental constraints there and how to optimize the designs. There's also been a lot of work on leg kinematics independently about how to choose different morphologies, different parallel or serial configurations to get the best performance for a certain task. There's also been a lot of work on platform morphology, and some of the work by myself and my lab mates has been in each of these areas. We've also looked at some work that couples some of these together, including coupling motor performance with drivetrain gearbox selection. This is a paper from a very long time ago, and you've obviously continued a lot of this work even to the present day at Ghost Robotics. And the work that I've seen that combines the most of these elements to get a holistic picture of platform performance. One of the examples is Patrick Wensing and Zhangwei Kim's work on proprioceptive actuation. Wonderful work. And really for each of these components, there are many different parameters. So obviously one disadvantage of trying to study them all at the same time is that the dimensionality of the system gets very huge. But in particular, in this project that I'm going to talk about today, which was a project I did in 2018, 2019 at Penn, we tried to look at how the motor parameters and the work that the motor controller is doing at the very lowest level can interact with the task that the robotic platform is trying to solve. So at the same time, we were developing these custom actuators for Ghost Robotics, and you can see on the right, just some examples of different kinds of impedance being simulated in software. There are lots of different types of brushless motor controllers, fewer available then than there are now. And I certainly don't want to give the impression in this talk that I'm, a real expert on motor control. My expertise is much more on the mobility of the robots themselves. But we did develop these custom actuators, custom motor controllers, which honestly gave us a huge, that they were just very easy to use and produced very good performance for our initial direct drive robots, and that really helped get Ghost Robotics off the ground. The reason that I'm mentioning them here is that obviously since they were custom, we could try all sorts of different control algorithms for testing how the software on the motor controller itself can interact with the task at hand. So to talk about that first, let's quickly talk about a couple of commonly used motor models. So obviously, one on the very complex side, there's a detailed FEM modeling of the motor and the magnetic fields that are produced by the stator coils. The problem is that the results that you can get here are very accurate, but also very brittle, and there's not too much analytical insight about how changing different parameters can change the behavior. And it's also obviously very time and computation intensive to get any results. On the other end of the spectrum, very analytically tractable are kind of simple one dimension, one degree of freedom, brushed motor type of analysis. And we used this back in 2011, and we've been using these kinds of models for a long time to kind of just understand the performance of a single, RL type motor. You can see the kind of the simple equation down here that just shows how the applied voltage is related to the voltage drop across the resistive part, IR and LI dot. So I apologize that the I here is actually what looks like an I is actually iota dot, and iota is the variable being used for current here. But yeah, anyway, it's voltage drop across the resistor, voltage drop across this inductor, which is depends on the rate of change of current, and the back EMF. So that kind of is a very simple model of the electrical properties of the motor. And on the mechanical side, it's very simple that the produced torque is kind of proportional to iota, the current through the coil, and that's what produces the torque that accelerates the rotor. The deficiencies in this kind of simple model, even though it's pretty simple to study, is that there's really only one control input, and it turns out for a brushless DC three-phase motor, it doesn't really explain the full torque output, and it also underestimates the maximum power and maximum speed that's able to be produced by the motor. So we looked at a three-phase brushless DC motor model, and again, this is obviously going to be a simplification of what's going on in one of these motors. We considered, in particular, non-salient rotors and sinusoidal back EMF profiles. With various definitions, you can have kind of simplified equations of motion that look at first glance to be similar to the brushed motor case, but here the back EMF is actually in a particular direction. So this V here is now three-dimensional for the three phases, and the back EMF waveform basically is, gives you the three waveforms for the three phases as a function of the electrical angle of the rotor. And mechanically, it's similar to before, but there's an inner product between the back EMF waveform and the current in the three phases. So the one thing that's pretty standard, and we also used it to simplify here, is to transform the equations into the moving rotor frame. So basically there's some projection based on this back EMF waveform function into kind of two components. X is two-dimensional now, and typically the components will be called the quadrature and direct axes, the DQ axes. The rotor frame equations of motion don't actually depend on the rotor angle anymore, so that makes it very simple to use these for analysis and also implementation of controllers. What we have along with these kind of simple equations of motion are the thing that we focused on is the power constraint that comes in through as a kind of a voltage constraint on the electronics that are in use. So, while I talked a little bit about the work we did with direct drive robots, obviously with the robots that are designed to be very efficient, ultimately specific power really always becomes the most fundamental constraint, because you can always choose different gearboxes to move around the specific force constraint, but the specific power constraint is not obviously affected directly by gearing. So with the simplified model, we can think a little bit about how to control it to produce, maybe a desired amount of torque or power or whatever it is. So the first thing that you can do when you look at this equation is to kind of do a basic energy balance. So just take the equations of motion in the first row over here, and if you multiply with IQ and ID, the X transposed X dot, this is kind of like eventually giving you an energy balance that the input electrical power is converted on one hand to joule heating, mechanical output power, and some transient power depending on x dot. But in equilibrium, it's very simple that, either you get mechanical output power or you get Joule heating. So obviously minimizing the Joule heating is important to keep efficiency high. So conventional control strategies, the kind of most common one is to do feedback torque control in these DQ axes using current sensing. So typically this is kind of diagonal in the sense of what I mean there is that the voltage applied on the Q axis is proportional to the or is only using the current in the Q axis as input, and similarly, and only trying to control the current in the Q axis. And similarly, the voltage on the D applied on the D axis is only trying to control the current in the D axis. And the usual goal based on, as you can see from the energy balance, that if we want to minimize the Joule heating, then we had better try to just set the second component, the direct current, to 0. So that's typically what's done in these torque controllers or current controllers. Another kind of simple strategy that could be considered is what we are calling the voltage control strategy, where only the first component VQ is used to control the voltage on the Q axis to try and produce the desired amount of torque. And this is obviously a simplified version of the first one that is less commonly used. So one thing that we wanted to try here is just at a high level to see what we can do by departing from these strategies, which usually control each of the axes independently, is to try and couple the D and Q axis control to kind of produce some result that is ultimately really dependent on the task that is trying to be satisfied, and not necessarily always try to set the D axis current to 0 necessarily. So if you recall the dynamics of the current, they take this form. And we can note from this equation at the top that if we're in equilibrium, obviously x dot will be set to 0. And based on what remains in terms of we get 0 equals A times the equilibrium x plus the equilibrium U divided by L plus the back EMF term. By looking at the structure of A inverse, what we get is a simple equation where, really what we can do is try to optimize the equilibrium x by choosing U with that sole objective and not necessarily setting the D axis current to 0. So the idea here is to use both the D and Q axes to try and align the input voltage with this vector R that we've defined here when in equilibrium. So this very kind of dumb strategy, we called it some kind of angle control. And basically the result it has is that it really seems to produce the peak power when in a lot of different simulated cases with these dynamics, simplified dynamics. So let me just explain what's going on in this plot here. So on the horizontal axis, we have the motor kind of rotor speed, omega. And on the vertical axis, we are plotting, since we're voltage constrained, we're assuming we're in a voltage constrained, power constrained scenario, the magnitude of the applied voltage is kind of fixed. And what we can really change, or any controller is able to change at all, is kind of the angle of the voltage signal, which is the kind of the arctangent between the voltage on the Q and D axes. So each of these different strategies will choose a different kind of phi, this angle quantity, as the speed of the rotor changes. So in particular, the dashed blue line, which is voltage control, always sets this angle to 0 because we picked that kind of simplified strategy just to show what happens if you just completely ignore what's going on in the D axis and only apply voltage on the Q axis. The torque control strategy, based on the EMF, the back EMF constant of the motor, must produce in equilibrium certain amount of voltage on the D axis to set the D axis current to 0, and that's kind of reflected inevitably by what's going on in the yellow line. And in contrast, the new strategy, the green strategy, the angle control strategy, really does not care about the d-axis current too much. It just really tries to maximize the power, the equilibrium power produced by the motor. And you can really see in this picture that the green line exactly follows the contours of the power production, which are the contours in blue over here. And it's visually very clear that it's trying to maximize the power for any given motor speed on the horizontal axis. And this peak power is actually exactly also you basically get the same trajectories for peak torque, because we're picking a different omega for each point on the horizontal axis. The torque times that omega is really the power. Yeah, in both of the power and torque cases, we get for a certain omega, we get higher power and higher torque with this simplified new strategy. The disadvantage of this, obviously, is that since we are not setting the d-axis current to 0, we get more heat production, but over some amount of the state space that we're looking at, the amount of heat production is at worst only 14% more for the existing motor. The other thing we looked at a little bit is let's consider fixing for one of these objectives, which is peak torque, and look at the advantage that this new strategy gives us over the conventional strategies, whether it be the voltage control or the torque control. And the contours that are plotted here are the ratio of the peak torque of, in blue, the voltage control divided by the peak torque of the new angle control strategy. And you can see most of these contours are smaller than 1. And similarly for the peak torque produced by the torque control strategy divided by the peak torque produced by an angle control strategy. And again, all of these red contours are smaller than 1. So we wanted to see how the advantage, this kind of defined as the peak torque ratio, depends on the design of the motor. And the axes in this plot are the back EMF constant on the horizontal axis and the electrical time constant on the vertical axis. And what we really see is that this strategy seems to have the most effect to the upper right of this plot, which means higher back EMF constant and higher electrical time constant. So now let's take all of this and try and make it relevant to robotics with a simple kind of task where we can visualize how something like this kind of newer control strategy might be useful. So we made a 1 degree of freedom experimental setup, which I called an inverted hopper, where really there's a motor sitting up top controlling the position of a vertical position of this mass using a string. And for this paper, we did do some inverted hopping trials where the position of the mass was being tried to be controlled by either letting it by kind of letting it bounce up and down. But for this presentation, I'm just going to go over braking trials where the task was, the mass was being dropped when the motor was freewheeling, and then the motor would be turned on. We would test how quickly we could make the mass stop. So as you can imagine, this is a pretty kind of power demanding task, specifically negative power. And what we found by kind of, since it was, easier in our empirical motor controllers to basically change the set points of the desired Q and D axis currents, it's sort of completely reworking the software. That's what I did. And just to show that it's not necessarily setting the d-axis current to 0 that produces the best results. Setting the d-axis current to something non-zero produces faster stopping in this kind of simple braking test, and kind of suggests to us that maybe departing from the conventional decoupled sort of diagonal strategy might be helpful in a lot of robotic tasks by giving us stronger performance when it might be most needed. So I'll stop here. I just wanted to summarize the high-level takeaways that I wanted to get across here. So the first is that kind of task-based control. So changing the control strategy for the actuator based on the higher-level task that is attempted to be solved, somewhat kind of coupling those two systems, can help us get closer to fundamental limits rather than kind of decoupling all of these systems. While this particular controller is just an example, what this kind of suggests is that we might want to rethink the interface that we have to the motor controllers and to our actuators. Instead of just commanding desired currents or desired torques, maybe we want to communicate something more about the task so that the motor controller is more free to choose a different control strategy to really get the best performance out of the motors that's possible to solve a certain task. And lastly, I showed kind of how the advantage of a kind of one of these control strategies with more freedom can depend on the design of the motor. And so I see that there could be a lot of opportunity for co-design type of tasks where both the performance of the controller itself, as well as the design of the motor, are worked on together to really get optimal performance for robotic tasks. I would like to thank you all for your time, and I look forward to interacting in the workshop session.